This video is just going to focus specifically on alkanes. So if you remember, alkanes are also known as saturated hydrocarbons, meaning they all have single bonds and you have as many hydrogens as possible on that molecule. So all carbon-carbons are single bonds or sigma bonds. If you remember sigma and pi bonds from 161, they're all sigma bonds, meaning they're just sharing 2 electrons. So the formula for any alkane, not cycloalkane, any alkane is going to be CnH2n plus 2. Okay, so this one here, this is ethane. It has 2 carbons. So it would be C2H, 2 times 2 plus 2 is 4 plus 2 is 6. So it's C2H6, and this is what the molecule looks like. Now, we're going to start seeing these triangles, like this is a triangle and this is a dotted line. Those are actually how we represent 3D molecules. So I will show you how to draw these in 3D. Not quite yet, but we are going to see some 3-dimensional drawings because the 3 dimensions actually affect how things are going to interact. So there are a bunch of different ways to represent structures in organic chemistry. So we are going to look at these 5 different ways to represent organic structures. And for each of these, I'm going to use the example of propane, which is C3H8. So this is for alkanes, and it does apply to all of the other ones, but I'm going to show you how to do each of these drawings or types. Okay, so the first is a complete structural drawing. Okay, so the whole structural drawing is really just a Lewis dot structure. Okay, it shows every single bond. You draw them all out. It looks like this. Remember, Lewis dot structures don't have to be correctly oriented in space, meaning you do not have to draw it correctly in, like these would all be tetrahedral. So 109.5 degree angles, they look like they're 90, and that's because you're really drawing in 2 dimensions. So the Lewis dot structure is really all you're going to do for a complete structural drawing. Now we can also do a condensed structural drawing. Okay, so we're going to make it a little bit smaller, a little bit easier to use, but it still shows the structure. So all I did to get to the condensed structural drawing is collapse the hydrogens that are bonded to carbons. So instead of drawing every single hydrogen out, we write CH3 bonded to CH2 bonded to CH3. Okay, so this is the condensed structural drawing. It still shows how they're connected. We just assume that all of those hydrogens are on the outside. So this is a carbon that has 3 hydrogens attached, and it's bonded to another carbon that has 2 hydrogens attached, and so on and so forth. So this is a little bit smaller of a drawing to do, but it still shows the connectivity. The next we have the condensed formula. So we still collapse all those hydrogens onto the carbons, and instead of showing the single or double or whatever bonds they may be, we're just writing out the formula. So this is what we usually use when we're writing a balanced chemical reaction, because it shows me still the connectivity of the molecule, but it doesn't have any bonds shown. So I've got CH3, CH2, CH3. When I see this formula, I assume they're all connected in a line. I know this is an alkane because each carbon has 4 bonds on it. And this is the one that you're going to see a lot of the time, especially in organic. Now, why am I not condensing it all the way down to C3H8? And that's really because that doesn't tell me anything about the structure. And in organic chemistry, the structure matters. So writing out the formula in this way shows me how it's connected. Okay, you will also see, and this one will probably be new, a line, or it's sometimes called a skeletal diagram or drawing or structure, whatever you want to call it. But the line notation or the skeletal, each line represents a carbon-carbon bond. So what I'm really doing is I'm drawing the Lewis dot structure, but I'm only showing the carbon bonds. So each line is a carbon on one end and a carbon on the other end. Okay, and the way you do it is in a zigzag fashion. So I can see that this is 2 lines. So each end is a carbon. So there's carbon here, and a carbon here. Now, it doesn't show any of the hydrogens or anything, but in organic chemistry, we assume each carbon is full. Each carbon has 4 bonds on it. So if I know this has 1, 2, 3 carbons, I know this is a carbon that has 3 hydrogens around it. I know this carbon has 2 hydrogens because it also has 2 bonds, and this carbon has 3 hydrogens around it. So this is what propane looks like as a skeletal or line drawing. So what you're doing is you're really just drawing the bond between the carbons. Okay, sometimes these are hard to interpret, but you're going to get practice in the active chemistry. And finally, the 3D or the Vesper structures. So drawing in 3 dimensions. Okay, this is important to show how molecules can interact with each other. It shows you that this molecule in particular is not polar, and it can show that other molecules are polar. So if you remember from 161, and it's okay if you don't, any sigma bonds or single bonds can rotate. Okay, double bonds can't, they're rigid structures, but if it's a single bond, you can rotate those around. If I've got a molecule, I don't think I have one in here, but if you have a molecular model kit, you can see you can twist those if it's just a single bond. That's called rotation. So there's free rotation. Now, it's not a straight line like we draw in a Lewis dot structure. They're kind of staggered like they are in the line or skeletal drawings. So the way that we draw these in 3D looks like this. I do carbon, bonded to carbon, bonded to carbon. And then I show that I actually have the hydrogens in 3 dimensions. So the way that this structure works is each line means that that is in the plane of the paper. Okay, so if I had this molecule, I had a hydrogen, carbon, carbon, carbon in the plane of the paper. Okay, a triangle that is, or like a wedge that is colored in, means it is sticking out of the paper at you. So I have 1, 2, 3 hydrogens sticking out at me. And the hydrogens with the dotted lines are going into the paper. So they are away from me. So this is one way in which we draw 3-dimensional structures. This also applies in physics when you start drawing 3-dimensional structures. That whole solid is coming at you and the dotted is going into the paper. I won't get too hung up on these because I'm not going to have you draw a bunch of 3D structures, but you can show how they are in 3 dimensions. Okay, so back to alkanes, right? So the first 10 alkanes, I'm going to show you how to name these because we're going to learn the naming rules for alkane molecules. The first 10 alkanes are listed here. So you'll notice in the formulas, they change by 1 carbon each time. And then the number of hydrogens is 2n plus 2. So if I have 1 carbon, 1 times 2 is 2 plus 2 is 4. So the formula for 1 carbon is CH4. This is called methane. Carbon with 2 would be C2H6. This is the condensed structural formula because it would be a carbon bonded to a carbon, and each one has 3 hydrogens around it. That is called ethane. So what we do is we just keep adding on. So this is my molecular formula, and this is the condensed structural formula. And notice it just gets longer and longer and longer. Okay, the end ones are always CH3s. The ones in the middle are always CH2s. Okay, because they have 2 bonds and then a hydrogen and a hydrogen. Now the names after a while are actually really easy to figure out. So these are alkanes, meaning no double or triple bonds. So they all end in ane, A-N-E, methane, ethane, propane, so on and so forth. Now, after at 5 and above, you should be able to figure those ones out really easily. They're the same as geometry prefixes. Pentane, hexane, heptane, octane, blah, 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 blah. The first 4, though, I do have a mnemonic to remember the order in which they go. And my mnemonic is Mary eats peanut butter. I learned that when I took chemistry, and that's how I remember it. If you come up with another one, great for you. But the first one starts with M, E, P, and B. So 1 carbon is methane, 2 is ethane, 3 is propane, and 4 is butane. You do need to memorize those, and those are going to be the first 4. After that, like I said, they're easy to figure out. So it's based on the number of carbons. Okay. The other thing you'll notice in this chart is the boiling point. So as these molecules get bigger and bigger and bigger, they're getting longer and longer chains of carbons, they actually have a much higher boiling point. Now, not crazy high, right? These are really low here. This one's really close to water's boiling point, and then these ones have a little bit higher boiling points. So the bigger they are, the higher their boiling point is because they have more London dispersion forces. So if you think back to 161, the things that affect boiling points for covalent molecules is London dispersion forces, because these are all non-polar molecules. Okay. So London dispersion forces are the only things that attract them together. The bigger the molecule, the more polarizable. That means that those hydrogens, those electrons can like shift around and give you some charges, and then they can attract. So the larger the molecule, the more London dispersion forces, and the higher the boiling point. And this is true for all of our alkanes, or all of our long chain alkanes. So the last thing I want to talk about before we go into naming is what a structural isomer is. So isomers are just the same formula. So they would have the same molecular formula, but they are connected differently. Okay, so it would be here. What do I have here? This is butane. So I have 4 carbons and I can connect them all in a straight line, or I could do 3 and then I could have 1 branched off the middle. And these are 2 different structural formulas, but they have the same molecular formula. So they do actually have different names. Let me see if I can zoom in here really quick. Okay, so this is just called butane. 4 in a row is called butane. If they are connected differently, this is called isobutane. So it does have a different name. Now, you also need to remember that all of these single bonds can rotate. So this is not just like drawn differently. If I just drew this bent, if I drew it like a carbon bended down, that's the same molecule. But these are actually connected differently because if I wrote out the condensed structural formula, this one would be CH3, CH2, CH2, CH3. This one would be CH3, CH, CH3, and CH3. So they are actually connected differently. These are called structural isomers. Isomer meaning same formula, different connectivity. Okay. Now that actual connectivity does also affect the boiling point. So this boiling point trend up here was for straight chain alkanes. But as they branch, it's actually a lower boiling point just because they can't attract as easily. So if you start getting branches on there, they can't like all fit together very easily. So more branching means they have a lower boiling point. So this is pentane. And these are 3 isomers of pentane, which has 5 carbons. So this is a straight chain pentane. This one is called isopentane, has 1, 2, 3, 4, 5. But you see this carbon is branched off of one of the inside carbons. So this is a different connectivity. It has a branch off. And this one is even a different connectivity. I have a carbon in the middle with 4 carbon bonds and then all my hydrogens on the outside. This is called neopentane. But this one, if you look at the melting and boiling points, they get lower the more branches that you have. At least the boiling point does, which is really what we're focusing on. Okay, so boiling point goes from 36 degrees Celsius to 28 to 9. Okay, so the more branches, the lower the boiling point.